We have adopted in this course a novel perspective on maintenance decision-making. We began by defining the basic problem in maintenance, and we articulated the recurring maintenance decision. Then we internalized a language and framework called RCM in which to structure maintenance knowledge. We addressed two obstacles left unresolved by initial RCM analysis, namely the absence of a process for systematic update of the RCM knowledge base and the inability of current EAM procedures to deliver age data of sufficient quality and precision for reliability analysis. We showed how living RCM hurdles these impediments. Thus, we are prepared to perform the final step, reliability analysis and maintenance decision modeling. Our example concerns a fleet of mining haul trucks. We consider the RCM failure mode transmission fails. We learned in RCM to select a practical level of analysis. In this exercise, we do not concern ourselves with the reason for failure. There is no right or wrong analysis level. In some other context, we might focus on the failure of a particular gear or bearing, sealing, or lubrication mechanism. The modeling method itself is a general-purpose procedure that can be applied at any indenture level within an asset. Begin the exercise by downloading the data sample. The sample takes the form of a relational database containing age data and condition data. We can extract the zip archive in a folder on our desktop. The folder's name will be Files for Exercise 1 _CAT. The folder contains an access database called cat340t _mes and a text file called attach scripts. Minimize the folder for now. Next, we'll fire up a reliability analysis app called Exact for Modeling. Hit File and New. Then navigate to the folder Files for Exercise 1 _CAT. Name the file cat340t _WMOD. Hit Save. WMOD stands for Working Model Database. This is where we will build and test our predictive model. The first thing we need to do is to attach the database containing our sample to our working model database. Open the extracted folder on our desktop that contains our sample. There are 4 files in this folder. The database file containing our sample, called cat340t _mes. MES stands for measurements. The working model database that we just created, and a lock file that appears whenever a MS Access database is in use. The 4th file is the text file we mentioned that contains information and scripts that will assist us with this exercise. Open the text file. The first 6 lines contain an attachment script that we will use right now. Copy it to your clipboard. Switch back to the exact program and hit Modeling on the menu bar and Data Setup. Paste the script into the Setup Script text area. Examine the script. The first line identifies the database cat340t _mes containing our sample. The next lines instruct the program to attach 5 tables from that database to our working model database. Hit Execute and Save. Notice that the 5 tables we attached appear in the tree view in the left panel. Those tables contain our sample as well as other information related to the model that we intend to build. We can view these tables by double-clicking them. The inspections table contains our condition data. Column 1 contains the name of the truck unit. Column 2 contains the dates of the CBM readings. In this case, the condition monitoring method is oil analysis. Column 3 contains the truck's hour meter reading at the moment of the sample, which we call the working age. The remaining columns contain the candidate condition indicators to be analyzed for any probabilistic correlation with failure. We can quickly navigate to the data for any unit in the fleet by hitting the drop-down list. The events table contains the age data extracted from the EAM work order database. As in the inspections table, the first 3 columns contain the truck unit's ID, date, and working age. The 4th column contains the event, B for the beginning of a failure mode's life cycle, EF for its ending by failure, OC is the non-rejuvenating oil change event included because the reliability engineer suspects that OC events may be influential in the eventual predictive model. Scrolling down, we have the 3rd event type, ES, symbolizing a failure mode instances ending by suspension. Ending events are normally followed by a B or beginning event designating the start of a new life cycle for the transmission. The events description table defines the various event types. Should 2 events occur at the same date, the precedence column will tell the proportional hazard modeling algorithm which of them should be considered to have occurred first. Age-based analysis methods require correct chronological ordering. A CBM inspection event will be set internally by the software to 0, ensuring that an oil analysis in our case will always be considered to occur prior to any other event, such as an oil change that might occur at the same date. In some situations, such as automated sensor readings, the date-time format would be used in the date columns of the various tables. The table var description defines the candidate condition indicators. The final table in our sample database is named covariates on event. We know that the condition data related to certain events will revert to their initial settings. In this case, the events B and OC would have new oil initialized values for calcium and iron, although an oil analysis would not have been performed at the time of those events. The starting date and ending date columns allow the analyst to indicate different initialization values in different calendar periods. For example, a change in oil brand would lead to a different additive package and different reset values in the calcium and magnesium columns. In the case of vibration, one might insert differing values corresponding to the dates of non-rejuvenating events such as balancing and alignment. Examine the models table, which is an internal table in the working model database. It is not present in the sample database. It contains no records yet. That is because we have not yet begun building a model. The table will be populated automatically as we proceed. The only time you might access this table manually would be to delete certain trial models that you do not wish to retain. In the software, a trial model is referred to as a submodel. Submodels are tested for their predictive capability in the modeling process. The submodel that we retain will be exported for use by an automated decision agent. Now that we have examined the internal and external database tables to be used in the analysis and model construction, we can proceed with the first of 3 steps in the development of a CBM optimization model. Hit the Data Preparation and Enter General Data buttons. Now enter the project information as shown. You can copy and paste from the same text file as before. Next, we instruct Exact to assemble the events and inspections data into a single, virtual, combined table called C Inspections. Hit the button labeled With Covariates Complete. Open and close a table in the tree if the button is not active. Examine the C Inspections table. Note that the records of both tables, events and inspections, have been combined. They have been arranged in chronological order. The asterisks in the event column symbolize a CBM inspection event. In this example, all condition data is oil analysis data. The C Inspections table will be parsed, record by the proportional hazard modeling algorithm. It will attempt to recognize patterns in the condition data that correlate with failure events. The column HN contains the history number. Note how it incremented as a new life cycle began. The program has included the precedences in each record according to the way we assigned them to their event types in the covariates on event table. Also note that the condition data at the OC events were populated automatically by the program, again according to the assignments we made in the covariates on event table. The algorithm will not be misled by the initialization values artificially placed into the condition data columns for these non-rejuvenating events. A final comment regarding this table concerns the data and working age columns. Reliability analysis requires that they both increase monotonically. If, for example, the date increases in time but the working age decreases from one record to the next, this will constitute a data error. The program will flag this error, which must be corrected by the analyst. The technical name for the data containing this type of error is dirty data. Now let's begin the modeling phase of the analysis. Hit the Modeling button. Now hit the Weibull PHM button. Next, hit Select Covariates. We'll start by building a model with all 4 condition variables: iron, lead, calcium, and magnesium, present in the CBM data. Accordingly, enter ILCM for submodel name. Hit OK twice, ignoring the convergence warning, which is normal for small samples. The results of our first trial PHM calculation are displayed in a parameter estimation report. The first table shown is the summary of events and censored values. It tells us that of the 13 life histories in our sample, 6 ended in failure, 3 ended prior to failure, that is, they were suspended, and 4 units are currently in operation. These histories are said to be right-censored. They are referred to in Exact as temporary suspensions. They have been identified automatically by the software. In the table, Summary of Estimated Parameters, the first column lists the model parameters whose values have been estimated by the software. The third column, SIGN, means significance. The proportional hazard algorithm has indicated by Y for yes and N for no whether the variable has been found to influence failure probability. In row 2, shape is shown to be significant, meaning that the item's age is an influential risk factor in the model. In addition to age, iron and lead have been designated as significant. These parameter estimates are the result of having fitted the age and condition data to the proportional hazard model equation. The equation calculates hazard as a function of age t, shape parameter beta, scale parameter eta, the vector of significant condition indicator values z or z, and the vector of condition indicator parameters gamma. The next step is to try a different model by eliminating the variable whose impact on the probability of failure is the least significant. This would be the one having the highest p-value. It is magnesium. Close the PHM parameter estimation report window and hit Select Covariates again. Deselect magnesium. Age, iron, and lead are still significant, but calcium is not. Close the report. Hit Select Covariates and deselect calcium. After having successively eliminated non-significant variables, what remains is the iron-lead or IL model. This is a viable candidate PHM upon which to build our ultimate decision model. To be thorough, though, we should perform one more test in order to see if a model based on iron alone would be good enough. Hit Select Covariates. Move lead to the left column and generate a new proportional hazard model named I. The report tells us that this is also a potentially good predictive model. That is, iron alone is still significant. But will it perform as well? In the next step, we'll decide which of the two submodels, I or IL, should be retained and deployed for decision support. Hit the Comparative Report button. In the Compare drop-down list, select IL, the more complex of the two models. We always begin the comparison with the model having a greater number of covariates, that is, condition indicators. Transfer the I submodel to the right-hand column. Hit OK and examine the PHM parameter estimation comparison report. The N in the second column is telling us that the submodel I is not close enough in terms of a statistic called deviance to the base submodel IL. This means that this simpler submodel would be less performant than the IL model. That is to say, the IL model contains significant predictive information that is not present in the I model. We would be losing confidence by using I rather than the more complete model, IL. We'll therefore reactivate the IL model. Hit anywhere in the left window pane. Hit Modeling on the menu bar and select Select Current Model in the submenu. Then select the submodel IL. Hit OK. Notice that the current model trans-IL now appears in the title bar of the right-hand window pane. It may also appear in the title bar of the exact main window. Now hit the Modeling button, not the Modeling menu item. Hit Weibull PHM and hit the Summary Report button. The table Summary of Goodness of Fit Test report tells us that the proportional hazard equation is a good fit to the data we used in its construction. The test is known as the Kolmogorov-Smirnov test, which is reliable with large samples and relatively few suspensions. We've constructed an equation that gives us reliability as a function of age and condition indicators found to be significant. For predictive maintenance, we will also need the probable trajectory in time of those condition indicators. We do this by defining condition data states. The condition data changes or transitions from one state to another. Hit the Transition Probability Model button. Then hit Transition Rates button. Examine the iron bands and then the lead bands using the drop-down list box labeled Covariate. Exact has created a set of bands or transition states for lead and iron. These divisions or bands are used by the software to build a transition probability model. The transition probability model calculates the probability of transiting to another state during the next inspection interval. To create the transition bands, Exact has examined all previous condition data in the CBM database and determined reasonable boundaries to define the states. For example, normal, good, poor, marginal, and critical. This will add predictive capability to our model. Hit OK. Hit Transition Rates if the Display Survival button is inactive. Then hit Display Survival. For working age, enter 8,000. For observation interval, enter 200. Select Display Survival and hit the Report button. The survival probability matrix between 8,000 and 8,200 hours is displayed. The probabilities of iron changing state in the upcoming interval are displayed in a tabular format. For example, if we are currently in state 0 to 4, there is a 30% probability that iron will move to the next state in 200 hours. The report provides the probabilities of being in any state at a future time. These transition probabilities will be used in the prediction and decision model to be developed next. Normally, the analyst does not concern herself with the probability matrix since it is accounted for by the software. Hit Decision Model. Then hit Decision Model Parameters. Here we'll set the business conditions. We'll focus in this example on cost minimization as our optimizing objective. In the Replacement C box, enter 1200. In the Failure C plus K box, enter 6,000. For cost unit, enter a $sign, and for inspection interval, enter 250. Hit OK. When the cost function graph appears, hit the Full Report icon. The Condition-Based Replacement Policy Cost Analysis report appears. Examine the Summary of Cost Analysis table. It says that by adhering to the interpretive decisions of our model, we'll achieve a cost savings of 75% over a replacement only at failure policy. We will look at the actual decision model in a moment. Since optimal implies a balance or a compromise, we observe in this example that the expected frequency of intervention is slightly higher. In other words, we are buying low cost and paying for it, in a sense, with more preventive activity. To test the model, hit Decisions. Select all 4 units in the fleet. Hit Report. Hit the Full Report icon. As we successively hit Page Down, 4 sets of prediction graphs and data are shown, one for each of the 4 units in the fleet. In the next step, we'll put our model to work.